Hi, my name is Zach Ludwig, and today we're going to talk about conductors in an electric field and what happens when you put a conductor in an electric field. So first thing that you need to know is that conductors have what we call free charges. That means that conductors have charges within them that are allowed to move freely. And so they orient themselves in a special way when you place that conductor in an electric field. So we know that electric field, or these lines, always go from positive to negative. So one really important thing to know before I draw any field lines interacting with the conductor, we need to know that there are no field lines inside of the conductor itself. So you will never see any arrows in this conductor. So if field lines always go from positive to negative, then when a field line interacts with a conductor, the field line will hit the conductor on a negative charge. And we know that because field lines always go from positive to negative. So that means that there's a bunch of negative charges on the left side of this conductor. Now, if there's no field lines within the conductor, then those field lines begin again on the other side of the conductor. But this time they originate at positive charges. So now our conductor is polarized. Now one important thing that's kind of hard to show with the picture, but these field lines, when they interact with the conductor, they always hit the conductor perpendicular to the surface of the conductor. So theoretically, I should be able to put some boxes showing that these lines are perpendicular at every single point where it hits the conductor. And I could do that for all of these. Again, it's hard to show, but it's true that field lines always interact with the conductor perpendicular to the surface of the conductor. So now we have our polarized conductor. So what is important about this? Why is this important in our everyday life? Well, it's for safety reasons is one of the biggest things. So imagine that you're in your car and you're driving down the road and it's really stormy weather. If you want to stay safe and avoid being struck by lightning, the safest thing to actually do is to stay inside your car. And why is that? It's because your car acts like a conductor. And so there will be no electric field within the car itself, so you'll stay safe. Or another example is if you're in your car and you're driving and a wire, and it's very stormy and a wire falls onto your car and it's a live wire, one thing that you really need to do to stay safe, and this is crucial, is you have to stay in your car until somebody can come to help, because the car, once again, is a conductor, and even though that wire is live and it's touching your car, if you're inside the car, you'll stay safe because there's no electric field within the car itself. Okay, so we talked about circular uniform conductors when talking about their shape. But what happens when you have a conductor that's not a perfect circle? That's not one uniform shape throughout, or one that has pointed ends. So this is really interesting actually what happens. So you have all these charges within your conductor. So you've got some positive charges. You got two sets. You have a set over here and a set over here. Again, my drawing's not perfect, and so it might be hard to tell sometimes what I'm explaining, but I'll try to explain everything so it all makes sense. So when you have two charges that are the same, we know that they repel each other. Two positive charges will force each other in opposite directions like this. And that's what these solid lines are showing right here, is that these positive charges are going in opposite directions, or they want to. And same thing over here. These solid lines show them going in opposite directions. But charges in a conductor have another force acting on them. And this is the force that is parallel to the surface of the conductor. And that's represented by these dotted lines. So you have a dotted line right here, it's parallel to this surface, it's going out in this direction. Same here, same here, same here. What you notice is that the angle between the two forces on the non-pointed end is much less than the angle on the other end. Again, my drawing's not perfect, but that is what I'm trying to show. So what does that mean then? Well, that means that if there's a smaller angle, these charges on the non-pointed end have a greater net force in these directions, opposite of each other, which means that it is easier to spread them out. And so charges on the non-pointed end get spread out a lot more than the charges over here. So these charges, since there's not as much of a net force in opposite directions, all the positive charges accumulate at the pointed end of a conductor. Okay, so we know that charges accumulate on the pointed ends of conductors. So why is this important? Well, we have these things called lightning rods. Lightning rods sit on top of buildings. So you have your building down here. And what they do is they get all these charges that accumulate on the tip of these lightning rods. For the reasons that I explained just prior to this. So what happens is that during a storm, for example, what these rods do is they get all the charges from the building, they draw them up to this pointed end, and when you get enough charges in one point, some of those charges will escape, so they'll go out. Which means that you're taking less charge, you're drawing charge out of the building, away from the building. This is really important because if it's a big lightning storm, there's going to be less charge on the building, and that means that there's going to be less of a chance that that building gets struck by lightning. And so lightning rods are also there for safety reasons, and that's why it's important to understand how charges act in conductors that aren't a uniform circular shape. Okay, so to recap in closing, conductors have free charges, and those charges move about freely, and when you put a conductor in an electric field, those charges orient themselves on the surface of the conductor, so they move around to the surface. There is no electric field inside the conductor itself. There are no field lines. The field lines that do interact with the conductor, they end on a negative charge, and then they originate again off of a positive charge. And those lines are always perpendicular to the surface of the conductor. And a more pointed end of a conductor equals more charge, and that's where the charges will accumulate.